Good morning, good afternoon from wherever you're watching from around the world. Welcome to today's VMware Tanzu webinar. Today we're joined by a friend of the program, Cora Iberkleid. Hey, Cora, thank you for joining us today.
Hello, great to be here. Thank you. Thank you so much, AJ. Okay, so hi everybody. Thank you for joining today and for this session on modern Java performance. We're going to be exploring a few different mechanisms for accelerating your Spring Boot applications and also talking about how this shows up on Tanzu Platform. So as AJ mentioned, my name is Cora Iberkleid. I work as a developer advocate at Broadcom, and it's really my pleasure to be here with you today to talk about this very relevant and interesting topic. So I want to start by giving a very simple agenda. We're going to begin with why runtime efficiency matters, and then we're going to look at what Java and Spring Boot give us today, and finally, how Tanzu Platform helps us operationalize all of this. So first, what do we actually mean when we say runtime efficiency? There's basically four characteristics that we mainly care about. So one is startup time. So how long does it take the app to be ready? Then there's warm up time. How long does it take the app to reach peak performance? And this is important because even after an app can finishes starting and can accept requests, it usually needs some time, some to process some traffic and exercise different paths before it's fully optimized. We also have throughput and latency, meaning how much work concurrently can the app do before it starts to slow down. And finally, the memory footprint, how much memory the app consumes. And so if we can improve, one or more of these characteristics, then some of the benefits that we get, of course, are lower infrastructure costs, using fewer instances, having better density of those instances on the same hardware, potentially the ability to scale down very aggressively to 0 or 1 if the startup and warm up are fast enough. And this translates to not only cost savings, but also lower resource utilization and a better user experience. So I think this is a really great time to be talking about this topic because we've seen sort of a steady stream of efficiency improvements across Java 17, 21, 24, and now 25. And at the same time, within Spring Boot, we're also focused on making those JVM improvements easy and practical to adopt with really minimal work and minimal tuning. Now, most of the optimizations that you see on the screen happen before the app even reaches production, but one of these happens at runtime, and that's virtual threads. So that's where I'd like to start for the day. Virtual threads, the title of the talk I know said Project Leyden. Virtual thread is not part of that. It was part of another project called Project Loom. So it doesn't really fit the title, but it's really relevant to runtime efficiency. So I definitely wanted to include it. So virtual threads primarily improves throughput and latency. It's the only one of the strategies that we're going to look at today that does this with secondary benefits to memory. So to understand why it does this, let's think about how threading works. So here's just sort of like the view of your laptop, right? Your machine has a fixed number of CPU cores. My machine has 10 cores. And the operating system has a scheduler that can schedule the OS threads onto those cores, right? And so only threads that are doing something active will consume the CPU time. So if an OS thread is waiting for something, then the OS scheduler will unmount it from the core so as not to waste resources. So in the JVM, there's not a similar mechanism. There hasn't been traditionally. The JVM has traditional platform threads that are basically thin wrappers around these OS kernel threads. But when they block, they're just set aside to block. And the way that you can do more work is by creating more Java platform threads. But eventually, you're going to run out of physical resources, and you're going to need to add more hardware because the OS scheduler can't reach into the Java stack and help improve the efficiency, within the Java stack. So, what happened in Java 21? Java 21 added two things. It added a virtual thread scheduler that sort of mimics the same behavior that the OS scheduler does at the operating system level, but now inside the JVM. And it introduced these lighter, faster virtual threads. So now the application work runs on these virtual threads instead of the platform threads. And these virtual threads are mounted onto a small pool of platform threads, or as we now call them, carrier threads. So when a virtual thread blocks, it's unmounted from the platform threads, and that platform or carrier thread is free to run other productive work. So virtual similarly, right? We can scale by creating more virtual threads, but virtual threads are cheap. They're cheap to create, cheap to discard, and they're managed entirely by the JVM. So the result is that the blocking IO doesn't waste our more precious platform threads anymore, and you're going to get dramatically better concurrency. And because the Java virtual thread scheduler also maps the default size of the platform thread pool that it starts to the number of cores on your system, you also get more optimal hardware utilization with very little tuning. So, how much faster, how much lighter are these? Virtual threads are orders of magnitude faster than platform threads. You can see here microseconds start instead of millisecond, kilobytes instead of megabytes. So the JVM can literally start millions of them. And this kind of gives you this illusion of nearly infinite concurrent threads, even though your code is technically still blocking on those virtual threads. So when to use these? If you have applications that have blocking IO operations, so if they have, especially if you're in the imperative stack, like WebMVC, for example, in Spring, where your threads are waiting for databases or for remote APIs to respond, then virtual threads will help you. If your workload is more computational heavy, more CPU bound, then virtual threads won't help you very much. And then just one important note I wanted to include here is that if you are using the synchronized keyword in your code, there was a limitation in Java 21 that was, for the most part, addressed in Java 24. So if that's the case, then you definitely want to use Java 24 or higher. Java 25 now is LTS. But in general, maybe better to stick with a newer version of Java. So I want to show you this as a demo. And first, to set up this demo, the application that we're going to be using uses, here's just, the minimal requirements. As I mentioned, 24 is recommended for Java, but as long as you have Spring Boot 3.2, Java 21, and some imperative stack like the Spring Web Starter, then you can see this in action. So here we have in the code a synchronous IO blocking call. We're going to call a backend service that intentionally has a delay before it responds. And we're going to run it 3 times actually. Here's the configuration for the first 2 runs. So the top is going to show our baseline configuration. We're going to use regular platform threads, and we're going to tell Tomcat not to use more than 10 platform threads, just try to do apples to apples and kind of keying off of the fact that I do have 10 cores on my machine. When we switch to virtual threads, which we'll enable with one simple property, we're going to tell the virtual thread scheduler to max out at 10, so no more than 10. We already know that because it does the hardware utilization optimization, it's going to set the default thread pool size to 10, but because of the 10 cores on my machine, but we're going to tell it to not use any more than that. So those will be our first 2 tests. And then in our third test, we're going to see how much the virtual threads can do with less resources. So we're going to max out this pool size at 1, right? So we'll compare the 3 situations. Okay, so let's let this run. All right, so I have this one just pre-recorded for the sake of time. So this is just, I'm using the test run just to use test containers to start our backend service. And we're going to simulate 20 different clients sending a total of 60 requests, and each request will block for 3 seconds, intentionally so. So we would expect 9 seconds best case scenario actually, and 18 if they're all the threads are waiting on each other. You can see here that we're using regular threads, and the execution number is going from 1 to 10 for each of the platform threads that we've allowed. And the results show that in fact, this took 18 seconds. So threads are waiting on each other. And you can see that a quarter of them took 2 to 4 times the expected time, right? Because they're just waiting to execute. So we're going to go ahead and enable virtual threads with this simple property that meaning we're not using the property on line 2 anymore. We're going to run the same test again. And in this case, when we look at the log file, we can validate that virtual threads are in fact being used and the worker number is also just going between 1 and 10. And in this case, the test finishes in the best case scenario, which is the 9 seconds. Every request took 3 seconds by design because the backend actually delays. So this is pretty powerful. Now, if we can do it with apples to apples, what if we give the virtual thread scheduler only one physical core? So 1/10 of the resources that we gave it in the previous test. So we'll restart the application and we're going to rerun the same test. And you can see here again, virtual threads are being used and the worker is just always reusing that one platform thread inside the JVM to mount them. And again, 9 seconds, every request took 3 seconds. So pretty powerful to see the virtual threads do more with less hardware as well, right? So to take away from this, with this, if you're using an application for which this is relevant, then all you have to do is enable this simple property and you're going to get a lot of benefits. So you can level up your existing applications if you are writing new code and prefer the imperative stack to the reactive. If you were only considering the reactive for this performance improvement, then there's other reasons to use a reactive stack. But if this was the only reason, then you can stay within the imperative stack if you're more comfortable. Don't worry about writing blocking code and your performance will be improved. Of course, user experience latency, we saw the impact, reduced hardware as we saw, and we didn't do any tuning, right? So next, I want to talk about the other set of optimization. So this one happens at runtime, the virtual threads that we just looked at. All of the other techniques that we are going to explore happen before the application reaches production. So they're pre-runtime optimizations, and rather than focusing on throughput or latency, these focus on startup, warm up, and they also have an impact on memory footprint. So the main idea really that unifies all of these is that they try to reduce how much work the app does when it starts up or as it's warming up. Now, Java and Spring are dynamic by design, right? So and this flexibility, this dynamic nature makes them very powerful, but it also means that a lot of work is happening as the app is starting up. And that's why they're a little bit slower to start up, right? There's class loading, reflection, auto configuration, profiling, just-in-time compilation. So this modern approach to performance tries to shift some of that work earlier, either during the build or after you already have the jar file during a training run, so that the information that you collect can be reused in future startups. So before we dive into them, I also want to cover Project Leyden. Which of these are Project Leyden and which of these are not. So Project Leyden doesn't refer to a single feature. It's more of the idea or the direction of improving startup, warm up, and memory footprint, but within the standard Java execution model, within the JVM. So of the techniques that we're going to look at, extracted jar layout, CDS, or what it evolves into the JVM AOT cache in Java 24. These are directly in the path of Leyden. Spring AOT, we're also going to look at that, but that's not technically Leyden because that operates at the Spring framework level, not as part of the JVM itself. And then native image, which means compiling an application into a static binary, removes the JVM altogether, and crack, checkpoint restore, coordinated restore at checkpoint. Basically, it starts up an application and it captures a memory snapshot of the JVM. So it also works a bit differently. So those are not technically Leyden. So just wanted to make that distinction clear. And also kind of an overriding view of it is the different ways in which work is shifted left. So it can either happen, as I mentioned, during the compilation or packaging, or during a live training or recording run. And so here's a little bit more detail on each of those and where they fit into that. So we have the extracted jar layout, the Spring AOT, and the native image under build, CDS, and its successor AOT cache, and the check coordinator story checkpoint on the right-hand side under the training run. And there's generally also an alignment between what's part of Project Leyden and what's sort of more broadly adoptable and less restrictive, and native image and crack, which are very effective strategies. They're a little bit more, I guess, ex, I mean, ex, I don't know if extreme, but they take a different approach, not the standard JVM as I mentioned, but they also have higher constraints. Um, so we're going to focus on what's within Leyden or aligned with Leyden and more broadly adoptable. And just to kind of go a little more into detail before we just focus on the Leyden, is this table, credit Sebastian Deleuze on the Spring team for this work, showing that the native image with GraalVM, the JVM snapshot with crack, versus this the part of Project Leyden JVM with AOT Cache. The startup and the warm up improvements with native and crack are very impressive. But again, if with GraalVM, often you need to provide reachability metadata, and the compilation is slow. So if you can deal with those, it's probably a little bit more on an app per app basis. Then you can still explore that path. Crack is only Linux, not a problem, but the since you're taking a snapshot of memory, there is a chance that some secrets could leak. So you have to be careful with any passwords that might have been captured in that memory snapshot. Make sure they're different for production, that you refresh those, etc. And so the focus really from the Spring team and the Oracle team is on the techniques that are more approachable, especially as they evolve and they improve. The outcomes that they provide are approximating GraalVM and crack a little bit more every time. So the idea is to get the maximum benefit with the minimum restrictions. And so there's a lot of attention right now on JVM AOT Cache. Okay, having said that, let's do a demo. All right, so this is going to be our first demo. So I'm using OpenJDK version Java 25. That's the important bit, Java 25 here. And as an app, I'm just using the reference application from GitHub, Spring Pet Clinic. I just checked it out, and it's at version Spring Boot 4.0. So the first thing we're going to do is a baseline build. So this is your regular Maven package. Nothing up my sleeve here. We'll just wait for that to finish and produce our jar file. And we're going to give it a run and get our baseline startup time. Okay, so this started in 3.7 seconds. So let's stop that. And we're just going to record that information. Okay, that's our baseline on my computer for this particular application. All right, so let's go one by one. So we have to do the Spring AOT first, because that information will get bundled into the jar file. So here, all we have to do is say, recompile the jar file, and this time tell Spring Boot to process the AOT, and then package the application. So we'll give it a second to do that. And we're going to have a new jar file as a result. Okay, so let's look inside this jar file. So Spring AOT is basically trying to figure out the application context so that it doesn't have to do it during startup. So here we can see, I mentioned earlier that Spring AOT was I think I mentioned earlier, but it was a requirement for native image for GraalVM. But it doesn't, if even if you're not using native images, you can still use this standalone. But that's why you see the result of the AOT compilation as part of this directory called native image. So there's the evidence that this information has been collected and embedded. And the other thing I want to show you, just because I want you to be able to compare this to after our next step. But if we go into the manifest file, you can see that the main class here is the custom Spring Boot jar launcher. The start class is our Spring Boot application class, which is the pet clinic application. And there's no class path here because the Uber jar that we're building contains all of the library, and that's part of that jar launcher. So just something to note, keep that in mind. Okay, so we've got our new jar file with Spring AOT. So we're going to go ahead and start that up so we can compare that to our baseline. All right, so 2.7, a little bit of an improvement there. And we're going to also record that information. Okay, so we're getting a little better. So let's go ahead with the next strategy, which is extracting this from an Uber jar. So there is a jar mode tools facility with an extract command. That's what I'm using here, and I'm going to ask Java to extract the embedded libraries and put them and our new smaller jar file into a destination directory called target optimized. So let's look at what it did. So here I'm just looking at the two jar files. The baseline one is 66 megabytes, as you can see, and my smaller jar file in my optimized directory is now 888 kilobytes, so quite a bit smaller. So how did it get that small? So this extraction pulled out all of the embedded libraries from the Uber jar and put them in a directory called lib side by side with my new optimized jar file. And if we look inside, so now go back to that manifest file we just looked at, and you can see here that I don't have a main class and a start class anymore. The custom jar launcher has been removed. Instead, the main class is just declared as the Spring Boot application class, which is Pet Clinic application, and the class path is explicit here and pointing to the lib directory that's expected to be side by side with the new jar file. So starting up without having to unpack all of these jar files is much faster, or it's not much faster, it's a little faster. So let's see, how much faster is it? So let's go ahead and start the application. And we can see that here it is, 2.855 seconds. So this is also faster than our baseline, somewhat of a similar improvement as the Spring AOT gave us. So what's interesting is that these techniques are complementary. You can stack them, so kind of the better together idea. So let's go ahead and enable the Spring AOT, because we know that those native directories are in the jar file, and use our extracted structure. And so these two together, they give us a 2.269 second startup time. So let's write this one down. Go ahead and record this. And so you can see kind of a steady improvement, right? Okay. That's for the build time optimizations in producing the artifacts that we are going to start at runtime during the compilation and packaging stages, right? The build. So next we can look at what can we do if we actually did a live JVM run? What additional information can we collect during the startup of the application that we can extract, record, and reuse to make further startups faster? That's what the JVM AOT Cache idea is. That's how CDS started, and JVM AOT Cache is evolving and extending that idea. So we're going to go into this directory where we have our optimized smaller jar file and our lib directory. And we're going to run this command. So we're going to actually just start up the application. But we're going to go into a special mode called AOT record. And we're going to produce a file that we're naming it app.aotconf. And we're asking the JVM, we're asking Spring to get to a certain point in the Spring lifecycle called on refresh and then exit. So let's go ahead and do that. So we're expecting the application to start, collect information, and then automatically exit by itself. Okay, so it exited and it created this app AOT-conf file. So now we want to convert that into a cache that we can reuse in production. So we run this command, which has the AOT mode of create, and we're going to name the file app.aot, that output file. So now if we look at what we have in the directory, we've got our app.aot file. And so this is our JVM cache file, or JVM AOT cache file. So we can use this. And again, I'm always using that Spring AOT enabled equals true because of that, the idea of the better together. So here is the results of starting an application with both of those, with all of three features together, basically. So that's a pretty impressive improvement. So let's go ahead and note that. Oops. There we go. Okay. So so as far as startup time with very little effort, it's pretty significant. So as long as you're using, if you're using an earlier version with CDS and Java 21, then the impact of the last step may not be as dramatic. But if you're using Java 24 or 25, then you should see something like this. So now let's talk about warm up, right? That all kind of addresses startup time. So with warm up, we can rerun the last exercise that we did for the AOT cache, but without the on refresh signal to Spring to exit the application on that at that point of the life cycle. So let me copy this command. We're going to run a load test. Okay, so we're just going to start up the application again in record mode, same thing. And now we're going to send some traffic to the application. So we're going to let it run for these 15 seconds and just warm up the application, let it exercise some paths within it. And in general, the better you exercise an application, the more it is. We can do this, in fact, twice, give it a little more time. I don't know if that makes much of a difference, but we'll do it twice. And when this is done, we'll go back and create our cache. Okay, so we've exercised our application and we come back here, we quit the application and we do our next command, which was the AOT create. So now we have a richer AOT configuration that we've gathered with all of this warm-up data. So we're going to create our cache. And now when we restart the application, we go back here and let's see what difference did that make in terms of warm-up. So we'll let that run for 15 seconds. On the left, I'm going to compare it to the first 15 seconds. So let that finish. Okay, so what did we get here? So on the right, we have initially on the left, our first run processed 50,000 responses. You can see that on the bottom. And here on this one, we processed 56,000 responses. And the slowest on the before was 716 milliseconds. And you see a lot of things kind of in the red, so to speak. And on the right-hand side, we see the slowest was 280, so about half that, and nothing in the red. So much better performance more quickly, faster time to better performance, right? And of course, getting to peak depends on doing a full training, right? The better your training run, the better the results of this will be. But you can see it even here. So that's pretty powerful. Now, some things to keep in mind are that when you're using these techniques, there are, as I mentioned, some restrictions and some sensitivities. For example, profiles, environment variables, anything that changes by the time you get to production can impact the effectiveness. In particular with JVM AOT Cache or CDS, the cache file is very sensitive to changes in timestamps or file permissions. If you change your JVM version or vendor, you could invalidate the results. In fact, here we can do one test changing that JVM vendor. So here we'll switch. It doesn't matter which, I'm just a different JVM vendor than the one I was using before, and just restart that same application. And you can see that our start time is now 2.4, right? We were down to 0.7. So this shows that Changing that vendor may not have affected the extracted jar impact or the Spring AOT, but it looks like we lost the effect of the cache file. So just to, just something to keep in mind. Although the AOT, Spring AOT is also sensitive to profiles. So in general, you want things to be as similar when you're compiling, packaging, and doing your training run as it will be in production. So let's go to the slides again. Okay. All right, so we did our demo here. So just to recap a little bit of what we saw, we had the extracted jar layout, which took our Uber jar, took out all of those nested libraries, codified that class path and the start and updated the start class. So that was one technique. And then we did the Spring AOT and the AOT cache, not in that order, but so the Spring AOT, both of these are focused on moving work ahead of time, but Spring AOT operates at the Spring framework level, and the AOT cache operates at the JVM level. And the Spring AOT is making that app context a bit smaller, fewer dynamic steps involved, and the AOT cache is trying to catch a lot of that sort of just-in-time stuff that's happening more dynamically and cache it. And the last thing here, so here's just a view on Spring Boot, how Spring Boot facilitates the AOT cache training run by aligning it with the Spring application startup lifecycle. And you can either exit on refresh automatically or just let the application run and do your warm up. And just a recap of some of the sensitivities, and we did a demo of the JVM, changing the JVM vendor and how that can impact the effectiveness. So having said all of that, this is basically what we've seen so far is what's possible on a single machine, right? And so it kind of begs the question, how would you leverage all of these benefits at scale in your organization in a real enterprise environment? Because the hardest part is not necessarily proving that it works once, right? But how to make this repeatable and accessible across many applications. So that's where Tanzu Platform comes in. And so I don't know how if everyone's familiar with Tanzu Platform and in particular the Elastic Runtime, but in general, Tanzu Platform it's a platform as a service that really provides a strong experience for both developers and operators. So on the developer side, especially with the Elastic Runtime part of Tanzu Platform, the workflow is intentionally simple, right? So you push your application as a developer or as part of a CI/CD toolchain, you push the application and then the platform stages it. It assigns it a route. You go from code to URL basically without having to wire up the routing, the load balancing, or any infrastructure. And you also get pretty straightforward things like scaling, service binding, credential injection, and the app lifecycle in general is handled consistently by the platform. I also think about it as a platform for operators because it includes that lifecycle automation for the environment itself, for all of the virtual machines that it's running on, that the runtime is actually utilizing, the routing layer, the logging, the metrics, security updates, backing services is also kind of operationally elegant and easy to run. So your operation teams also can stay pretty lean even as the number of applications grows because the platform is standardizing and automating all of that repetitive operational work. And specifically for everything that we just demoed, the key component is the Java build pack, which is what turns your application artifact into something that is production ready. So it configures the JVM appropriately. It does memory calculations. It handles certificates, security providers. In general, it applies these sort of battle-tested defaults that enterprises need, right? So, and importantly, this build pack is where the Spring Boot efficiency features that we've been talking about get operationalized. So in the manual demo, we produced multiple artifacts, right? The cache file, the separate lib directory, the smaller jar file, and those artifacts are sensitive to changes. So it's also important to note that the platform by nature has parity between the staging and the runtime environment, right? So your class path timestamps, permissions, profiles, environment variables, even the services available. So you get really can maximize the discovery of things that can be cached earlier. All of that is sort of natural on the Tanzu platform environment because of its consistency. So here we can see kind of a visual of that. Both the staging where the build pack is operating and the runtime where your application runs in production are managed by the platform, and they have that parity of operating system, JDK. Everything about them is the same. So the way I think about it is that these optimizations on your laptop, you can see that they're very powerful, and then on the platform they become repeatable, right? And scalable. So you get this efficiency without the burden and without any risk. So using this is pretty easy. It's just a question of when you deploy an application, specifying if you want, for example, if you want to do what we just did in the terminal, specifying that you want to use Java 25 and then enabling the features that we saw. So you would Spring AOT enabled would enable the Spring AOT feature, and the AOT cache would enable both the extracted jar as well as the AOT cache. So we can look at a demo of this as well. And just virtual threads by design, they're not part of the build pack because it's really more of a developer decision to enable or not enable that particular property that we saw in the application file, but it will obviously be effective on the platform. So let's go ahead and do our Tanzu platform demo. Okay, so we'll do our baseline. So I'm just going to repackage our jar file because we had added the AOT configuration to it, and we don't want that for our baseline on the platform. Okay. So I'm just going to push the application. I need this minimal configuration, and go ahead and push our baseline app. And we'll just give this a minute to finish. But essentially, you'll see as the output starts to appear, you start to get an idea. I mean, beyond how easy this was, just a CF push, you'll start to see some of the sophistication that's built into the platform. And also consider that this is by nature also something that's centralized on the platform, and therefore it's giving you already a scalable, shareable way to do this that's governable and manageable by the operations team, right? It's centralized. So we can see here some of the optimizations in Java build packs for all applications. So we have the memory calculator, a certificate mapper, security provider, the JVM kill agent. These are just different optimizations that have been built into the build pack for turning Java applications specifically into runnable artifacts. Depending on the language that you're deploying, you would see similar optimizations for those languages, right? This is a polyglot platform. So we'll just give it a minute to finish here. Oh, the other thing I should point out also is that when we do these two tests, what we're looking at for is the relative improvement of the second run versus our first baseline run, because this platform is actually running on sort of not very beefy hardware. So it is, as you can see, it is a bit slow even to just push this, but that's to do with the hardware that it's running on. It's, as we call it, NICS basement. Um, so you can see here that, okay, 165 megabytes of memory. You can see here it has the default launcher, right? So it hasn't done the extracted jar yet. And if we look at the time it took, it's 7.6 seconds, right, to start up the application on this particular hardware. So if we're going to do the efficiency, all we have to do is add one environment variable to the deployment, enabling both our Spring AOT as well as our JVM AOT cache. And we can, I'm pushing the application again because I want the output to look similar, so we can follow it in the same way. You could just also restage it right on the platform. You wouldn't need to re-upload the jar file. So we'll see that in this case, the build pack is going to detect that the Spring AOT compilation was not included in the jar file. And so it's going to go ahead and do that calculation and update that jar file. And then it's going to extract it. And it's also going to do a training run where it's going to capture the cache. And it's doing all of this in the staging environment that If we were using services, if this application used databases, for example, those would be available for it so that all that information preloading, we wouldn't have to configure anything to avoid sort of early database interactions because our build environment doesn't have access to those services. We are doing this in an environment that has full parity with our production environment. So that's another benefit. So we'll just give it a chance to finish that training run. It's at 30 seconds, and then it should finish packaging that up and start it up. Okay, so we see that it's starting. And here we can see evidence, right, that it did unpack the jar file. We see our AOT cache file that it's using, and it has enabled the Spring AOT as well. And if we look at the startup time, now it's under 2 seconds, right? So we went from 7.5 seconds to under 2 seconds. So about almost a 4x improvement, right? So that's that's kind of what I wanted to show you. I have a takeaway slide here. All right. So that's the information that I wanted to cover for you. I hope that's useful and that you can put it to use right away. I think the takeaways are that if you are interested in improving throughput or the tail latency, then you can start with virtual threads. If you're looking to improve startup or warm up, then look at these improvements that are aligned with Project Leyden. And if you want to do this broadly across the organization in a safe and easy way, then the platform is really going to help you operationalize these without any burden and without risk across all of your applications. So I hope you found this useful. Thank you for much. Thank you so much for joining.
All right. Thank you, Cora. We do have a few questions here. How do startup speed and memory efficiency translate directly into cost savings and improved resource utilization in a modern cloud environment?
Yeah, great question. I mean, it goes back to those four factors that we talked about. Startup and warm up, for example, if you can improve those enough, then you can actually, when you don't have as much traffic coming into your application, you can just scale that down to zero or one instance, and that in itself will save you a lot of resource utilization on during low peak usage. And then as far as the density, if your every individual application instance uses less memory, and if you can increase the throughput through virtual threads, every instance can also handle more traffic, then you also need less instances even during peak times, right? So overall, at all times, you will be using less infrastructure, whether it's on premise or in the cloud. In fact, it also some of these also if you there's a talk from Devox Belgium that was I think in October or November of this year. Anna Maria Mihalcenu from the Java team and Moritz Halbritter from the Spring team gave a talk, and they showed some charts with the results of their test. Sort of the demos that I was showing, but they had one additional one where they showed the also the CPU time, and that was also improved when they had AOT cache and Spring AOT compared to baseline. I think it was like a third of kernel time also that was used. So it definitely translates directly to cloud infrastructure and how you're charged. Um, and of course, then the less infrastructure we're using, the better for the environment. That's that corollary. So I hope that answers the question.
That's great. Thank you, Cora. We have one more question here. Now, these are great for apps that are using Spring Boot 3 or higher, but what about those of us that are running older apps?
Yeah, good question. I have two answers for you. One is that if you are a platform user and you're using the Java build pack in the Tanzu platform, the Java build pack includes for Java 8 and Java 11, it has a performance JREs from Liberica that have backports of security and performance improvements in, I think, Java 21. So just by virtue of using that, you'll be using JVMs that by themselves offer performance improvements. And the other thing would be how do you get your organization to upgrade those apps more easily and more quickly? And for this, within, again, this is sort of within the Tanzu platform, there's also utilities for doing this. In the open source world, you can look to something called Open Rewrite, which is a technology for doing these semantic changes on your code. And it would use recipes for these different changes. But within Tanzu and from the Spring team, we have probably the most extensive collection of Tanzu and of Spring and Java recipes. So through this through a tool called Application Advisor, and so this will automate the upgrading of your Spring 2 applications to 3 and eventually to Spring Boot 4, so that you can start to take advantage of these newer techniques. So I guess the part of it is, yeah, relying on the performance-based backported JVMs, and then finding more modern ways to do the updates without causing too much of a burden for developers. So you can just automate the upgrade, test it, and then do a code review with a developer before you make that into your check that into your main branch.
And thank you, Cora. I think those are all the questions that we have here today. I'm not sure if you have any closing thoughts, but I do want to just plug a blog that you just released this week, Tanzu Platform, still the best place for enterprise Java apps. So if you guys haven't read it already, I will make sure to include the link so you guys are able to view this as well.
Thank you, AJ. No, it's just a pleasure to be here. Thank you for having me. Thank you for everyone who joined. And you can find me at Cyberclyde on X. If you have any questions, I'm happy to take them.
Thank you, Cora. Thanks to all of you guys for joining us today. Happy holidays. Wish you guys well during this holiday season. Safe travels. Enjoy the time with your family and stay warm. I know some people are in some colder places than we are over here in California. So stay warm. We hope to see you guys at our next event. Bye, all.
Bye.